The broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, I'm gonna wait about 30 more seconds for any people still trailing in. I see the numbers still rising a little bit. Okay, everybody, why don't we go ahead and get started? I want to thank everyone for coming out to the weeks 3-4 S2S webinar series. And as many of you are aware, this monthly series is co-sponsored by the OAR Weather Program Office S2S program and the NWS OSTI modeling programs. And I'm Mark Olson from the WPO S2S program. Today we have two really good talks, but before we begin, I want to remind everyone of the webinar series website, and I'll post the address in the box shortly, or you can actually maybe see it on the screen there if it's not too small. But I'll remind you that on the site you can find information on the upcoming talks, and you can add yourself to a mailing list to stay informed of notifications relative to the webinar series. And you can also access the recordings of past talks as well. And so one thing I really want to point out here is there's a form available here for interested speakers. So if you're interested in presenting a future webinar and spreading knowledge of your work, advertising your work as the case may be, we currently have spots available over the next few months, so we do encourage you to consider giving a presentation. I'd like to get some more spots filled over the next few months, so that would be great. Just please let us know. Finally, in this series, if you have questions for the speakers during their presentation, go ahead and post them in the discussion document. Right now there's a link in the chat box there. You can click on that. You can request access if you need be, and hopefully one of us will get that request and set that up for you. If you can't access it or whatever, let us know, and if you can't address it immediately and you have a question, we can have a verbal question as well. So today our first speaker is Kathleen Pegion, who will talk about using machine learning to understand predictability of Southwest U.S. precipitation. After that, Jensen is going to be discussing recent enhancements to the METplus package. So let's go ahead and get started with Kathy. And I'm going to switch over to make her a presenter here. And whenever you're ready, Kathy, thanks.
All right. Thanks, Mark. Hopefully everybody can see. Should be coming up. All right. Mark, can you just confirm it's that everybody can see?
It still says waiting to view Kathy's screen.
Okay. It says it's showing on mine, so let's give it a second.
That's interesting because we just did this in practice.
Of course, works in practice.
So Mark and Kathy, I can see it, and I can see Kathy's.
Yeah, just came up on mine, so.
Okay, great. All right, let me move the little thing here and hopefully get a pointer up. All right. Well, thanks to Mark and WPO for the opportunity to present on today's webinar. I'll be talking about understanding predictability of daily Southeast U.S. precipitation using explainable machine learning. And this is work from a paper that was recently submitted with my co-authors Ben Kurtman and Emily Becker to the new AMS journal on artificial intelligence for the Earth system. So to motivate this work, I'll start by talking about the current prediction skill of our subseasonal prediction systems for precipitation. And this is showing you from the average anomaly correlation over North America for week 3-4 forecasts from a collection of the sub-X models, as well as a multi-model ensemble. The different colors are showing you different seasons. And you can see here that even for the best seasons and best models, that the skill over North America for precipitation at week 3-4 timescales is actually quite poor. And so we really want to be able to improve on that. There are some hopeful signs, even though that overall skill is poor. When you think about whether the low skill forecasts are useful, it depends on the user and applications. When you look globally, you see that some regions have more skill, but particularly over North America, that skill is low, whether you look at it aggregated or whether you look at that by grid point. But the one useful, I guess, sort of hopeful piece of information here is that some times are more skillful. And this is illustrated by looking at the pattern correlation over North America of week 3 precipitation. And so this is a histogram of those pattern correlations. So what I've done is to take all of these forecasts. This is from a particular model. As an example, you take all each individual forecast of week 3 precipitation. You take that pattern over North America, correlate that with the observed pattern, and you get this histogram of correlations for all the forecasts. And you can see that the majority of them have very low skill, but the hopeful information is that there are times when there's higher skill. And so this points to the idea of forecasts of opportunity, that there are times when we have higher skill of precipitation, and maybe we can take advantage of that to improve our subseasonal forecast. So we're going to focus in this particular presentation and study on a particular region to try to see how we can make better and more useful S2S precipitation forecasts. And that region is the southeastern US, shown by this map. And our goal will be to identify forecasts of opportunity. And really identifying forecasts of opportunity comes down to a predictability problem. And we need to really get at that, we need to better understand our sources of predictability. So we're going to look into that in much more detail for this particular region. So what are the sources of predictability for Southeast US precipitation? In the literature, if you look, there's a large collection of potential predictors for Southeast US precipitation on S2S timescales. Evidence that the Atlantic multi-decadal oscillation, Pacific decadal oscillation, that they can actually impact subseasonal and seasonal variability of precipitation in the Southeast US. And so the North Atlantic oscillation, MJO, North Atlantic subtropical high, weather regimes over Pacific North America region, and a newly identified source of predictability called the mid-latitude seasonal oscillation. So we have this whole collection of potential sources of predictability, and we really need to figure out how to disentangle them in order to understand how they contribute to predictability of Southeast US precipitation, which ones are most important, and how we can use them for forecasts of opportunity. And so we're going to use explainable machine learning for that. Before I go into the details of the machine learning, I want to highlight two of these sources of predictability, because these are the ones that come out as most important in the results from our work. The first is ENSO. It is well known during El Nino winters, La Nina winters, the impact that they have on Southeast US precipitation, the changes in the circulation over North America due to El Nino and La Nina, impacts the jet stream and the storm track, leading to wetter conditions over the southern tier of the US during El Nino, and drier conditions over the southern tier of the US during La Nina. That addresses the winter predictability. In the summer, the North Atlantic subtropical high has been identified as an important source of predictability for Southeast US precipitation. And in particular, when it shifts relative to its climatological position and extends its western ridge further out over the southeastern US, you get subsidence in the southeast, and that leads to decreased precipitation. And when it's less extended over the southeastern US, and its circulation brings moisture in from the Gulf of Mexico, that leads to enhanced precipitation over the southeastern US, and again, particularly in the summer. And there's also some studies that have identified that the SSTs in the Atlantic multi-decadal oscillation region, the North Atlantic SSTs, have an impact on the variability of the North Atlantic subtropical high, and so can help to alter those changes in the North Atlantic subtropical high on S2S timescales that can affect the precipitation. So in this project, we're going to focus on this very specific problem to find out how well can we predict the sign of Southeast US precipitation anomalies if we know the values of our predictor fields or indices perfectly. And so this gives you an example of the precipitation anomalies. This is the observed precipitation anomalies in winter and summer. So that's winter is DJF, summer is JJA. And so the green indicates when we have above normal precipitation anomalies, the brown when we have below normal precipitation anomalies. We're going to take two approaches. The first is to take the indices of these large-scale climate phenomena that have been identified as sources of predictability, and use those as predictors to predict above or below normal precipitation. And we'll find that those don't work very well. So then we move on to using gridded fields as predictors, and we find that that works much better. So to start with our index-based predictions, again, using indices representing these large-scale climate phenomena, we're going to use two different models. The first is the most basic model that we can use for this problem, and that's a logistic regression. We'll give the different indices as the input to our logistic regression, and then we will get an output of above normal or below normal, above normal, yes or no, below normal, yes or no precipitation. And so logistic regression represents a baseline, simplest possible model for this classification problem of above or below normal. And so you can think of it as analogous to linear regression for a problem that is designed to predict, say, like an index or a specific value. In this case, since it's classification, we use logistic regression. The logistic regression can represent linear relationships between these indices and the output categories. The other model that we'll use for our index-based predictions is a fully connected neural network. And you can think of this as a logistic regression where we've added a hidden layer between the input layer and the output layer. And this hidden layer contains the ability it has these nonlinear activation functions, which allows this model to represent nonlinear relationships between our input predictors and our output predictors. And before these categories are determined in these models, that there's actually a probability that's produced of above or below normal precipitation, and then the category is selected from that probability. And so we'll actually use those model probabilities in the same way that we use model probabilities from ensemble prediction systems. So neural networks are trained using stochastic methods. So there's a slight difference in initialization in training the models. And so you can get slightly different models. So what we do is we train 100 different models for the logistic regression and for the fully connected neural network. And so this shows you a histogram of the accuracy of those models for the logistic regression on the left here, the fully connected neural network on the right. And then the top panels, we do this separately for winter and for summer. Summers in the lower panels. And what you can see is that the accuracy of these is 50%. So what you can see, we can determine from that is the models are no more accurate than flipping a coin. So these are not accurate models for predicting Southeast US precipitation sign anomaly signs. The other thing I'll point out is that this, while the fully connected neural network was a more complex model, it does not seem to be any better at predicting the sign of Southeast US precipitation than the simplest possible model. And this points to the problem being the use of these predictors, these index-based predictors for predicting Southeast US precipitation. Well, we have this not very accurate models, but maybe there are still forecasts of opportunity. And so we can use the model probabilities to quantify that. And so these are reliability diagrams. And what the horizontal line on a reliability diagram is telling us is that the model probabilities are not reliable. So these index-based models are neither accurate nor reliable for predicting the Southeast US precipitation sign. And so we're going to move on to a different methodology to address this question. So now what we're going to do is use, instead of the indices, we're going to use gridded fields of the different variables that went into these indices. But now each and every grid point of each of these fields becomes a predictor in our neural network. And so then we have a bit of a challenge because we have many, many predictors. And given the sample size and computational constraints, it becomes difficult to then train a fully connected neural network with so many predictors. This is often addressed in machine learning by using a convolutional neural network. You can kind of take advantage of the spatial coherence of the data to kind of do a dimensionality. I think of it as a dimensionality reduction to the problem to make it more tractable for making these predictions. So we go through a series of convolutional filters, which reduces the dimensionality of the data with the idea that it's pulling out the most important features to identify to be able to make the prediction of above or below normal precipitation. So once you've done this sort of convolutional dimensionality reduction, you can then put in your fully connected nodes, and then you get the forecast probabilities followed by the output categories. So if we look at the accuracy of this model using the gridded fields, we see that for winter, it's about 70% accurate. For summer, it's about 60% accurate. And we can see that the forecasts are reliable. So those forecast probabilities indicate that when the model has a high probability, the model is also going to be, the above normal or below normal precipitation is more likely to occur. So that means we can use the probabilities from the convolutional neural network to identify forecasts of opportunity. And then to further understand the sources of predictability that led to those forecasts of opportunity. So now we're going to take a look and understand what those sources of predictability are. So we're going to focus on forecasts for positive Southeast US precipitation anomalies. And we're going to pick the forecasts that were confident, the ones that were said greater than 80% chance, and were correct. And so just to orient you, this is showing you and we're going to focus on winter to start with. So this is showing you the OLR for these positive, confident, and correct forecasts. And you can see negative OLR anomalies over the southeastern US. So that makes sense with our positive precipitation forecast. And you can also see, this is a composite of all of these confident and correct forecasts. And so you can see there was also some tropical OLR anomalies that are also probably related to this as well. So how are we going to take these confident, correct forecasts and understand what those sources of predictability are? We're going to use explainable machine learning methodologies called Layerwise, a methodology called Layerwise relevance propagation. And the way this works is that once the network is trained, you can give it input predictors, go through the network, get the output forecast, and then you can go back through and identify for each layer and node of the network what the previous layer and node contributed, what relevance it contributed to the value of a given node. And you can go all the way back till you get to the input. And because of the way in which the relevance is, the way this is applied, the relevance is conserved throughout the whole network, so that once you get back to the input, you have a measure of how much that input contributed to the output. And so this is applied to each forecast individually, and it allows you to get a heat map that will show us our relevant variables and grid points that contributed to a given prediction. And so if we do this for every forecast, we can then look for the consistently relevant predictors across those many inputs and identify those as our sources of predictability. So now we're going to take a look at the relevance for some of our fields. So looking at the winter, 850 hectopascal geopotential height and zonal winds. And again, this is for forecasts of positive precipitation anomalies that had high forecast probabilities and were correct. And so these were the highest relevance occurred for the zonal winds and the geopotential height at 850. And you can see these regions here are where that relevance was highest. The way that relevance is normalized, you can compare between fields. So this is showing you that the highest relevance occurred in this region, and then the other values of relevance you can say are relative to that highest relevance. So you can say that, for example, this point is between 40 and 50% of the relevance of this point that had the highest relevance. Of course, the relevance, it's hard to make physical sense of what it's telling us unless we apply some physical information to it. Relevance is a unitless quantity. So what I've done is to add composite anomalies on top of the relevance so that we can try to understand physically why these regions came out or sort of popped out as most relevant. And so what you can see is that your highest relevance is associated with westerly zonal wind anomalies and low height anomalies such that the circulation would bring moisture into the Southeast US region. So this seems physically consistent with the idea of these being good predictors of Southeast US precipitation for the winter. So now let's look at the SST and understand how it contributed. If you do a composite of these positive precipitation forecasts that were correct and confident, you get SSTs that are consistent with El Nino. We don't see relevance, any relevance that is in the scale here on this map. And what that's telling us is that none of the SST predictor or grid points had a relevance that was more than 30% of the relevance of our circulation. So that's telling us that the circulation anomalies are what's most important to making these successful predictions and confident predictions according to our neural network. And this kind of makes sense. We gave the neural network perfect predictors. So I gave it the exact circulation anomalies that were known to happen, whereas in a real forecast, there would have had to be some lead time and there would have been some errors in those circulations. But in this case, we gave it the perfect, sort of a perfect predictor type situation, and that's analogous to like a zero lead time. So it's not surprising that the circulation came out as most important. And so that's not to say that the SSTs are not important, but that the circulation is what's dominant in this sort of short lead time perfect predictor type scenario. So now if we look at the summer predictions. Again, positive precipitation anomalies, confident and correct forecast. We see that the OLR composites show us a negative OLR over the Southeast US, and so that's consistent with our positive precipitation anomalies. And if we look at the relevance for the circulation, we see relevance highlighted in this region for both the geopotential height and the zonal winds. And if we overlay the composites, you can see that this is related to the variability, appears to be related to the variability of the North Atlantic subtropical high. So this is shifting the high around, and the winds associated with that lead to easterly winds that would bring moisture into the southeastern US and thus increase the chances of precipitation. If we look at the SSTs, we see that the SST composites are strongest here in the North Atlantic, and we see some relevance values in this region that are between about 30 and 40% of the circulation relevance. So this indicates that the summer is precipitation anomalies are possibly related to the North Atlantic SSTs and how they might impact the North Atlantic subtropical high. So to summarize and conclude, using indices of large-scale climate phenomena is insufficient to skillfully or reliably predict the sign of the daily precipitation anomalies in the southeastern US. The global gridded fields as predictors are accurate and reliable, allowing us to identify forecasts of opportunity. The convolutional neural network that we use can identify physically relevant relationships between large-scale climate and daily Southeast US precipitation. We found that the local circulation is most important in this perfect predictor scenario that we set up. We found that in the winter that the predictability is related to ENSO, that's consistent with well-known understanding, and that in the summer we found that it's related to the North Atlantic subtropical high and North Atlantic SST variability. So this is kind of think of it as a proof of concept of the ability to identify sources of predictability and forecast of opportunity for Southeast US precipitation. The next steps are to expand this to other regions. Other regions use what we've learned about the SSTs as predictors, particularly the summer North Atlantic SSTs, to kind of guide some sensitivity experiments with global climate and prediction models. We could do real prediction with a lead time and understand how those most relevant predictors change over a subseasonal to seasonal forecast. So as we go further out in time, we expect that the circulation becomes more and more uncertain, but that those SSTs probably have a much stronger relevance to the correct continent forecast. We can also use predicted values of the large-scale climate fields from the sub-X models, and then understand how the errors in those fields are leading to errors in the precipitation forecasts. And then finally, our ultimate goal is to predict extreme precipitation events during a weaker season and be able to identify forecasts of opportunity for extreme precipitation. That's all. Thank you very much.
Well, thank you, Kathy. There is, let's see, one question so far in the document here, and says, could you touch on how you determined what hidden layers you used in your FCNN neural network?
Yeah, so I did a lot of testing of how many hidden layers. I started with a much larger number of hidden layers and kind of found that no matter what I did to tune the model, I was always overfit. So I kept trying to, so basically I just reduced the number of hidden layers and nodes in hidden layers until I found a model that could be, that could be fit, was not overfit, that it, it seemed to generalize to both my training and validation data properly. But it was very much a trial and error type approach to determining the architecture of the model.
Okay, I'm going to go ahead and switch the presenter over to Tara. We're out of time. I see another question in the document there. If you could take time to go in and take a look at that, Kathy, that would be great.
All right, I'll do that.
Okay, so Tara, let's see. I have made you presenter.
Yes, and I have clicked on presenter or present my screen. Can you see it?
Yes, we can.
Okay. Excellent. So thank you for giving me this opportunity to introduce some of the recent enhancements to METplus for evaluation, both of weeks 3, 4, and further out into S2S. And this work has been performed not only within the DTC, but also through projects that have been granted to NCAR and to some of our collaborators. And I'll call the collaborators out as we're going through the presentation. What's going to be covered here is some of the new process-based metrics that are in METplus version 4.1, which was released in March, and then talking about some of the work that we've been doing with understanding some of the statistics and how they're used within the CPC, and then upcoming developments. I do want to point you to the METplus training series. We just ended that series, but the link is here for a full record of all of the presentations that were given during the 19 one-hour sessions that we gave between November and last week, and including recorded presentations. And there is a specific recorded presentation from session 18, April 19th, that covers in much more detail all of these metrics that are in METplus version 4.1 and how to run METplus to use those. And then over here on the right-hand side is just a screenshot of all the use cases. In other words, the set of configuration files, sample data, and documentation that are available on the METplus users guide. So we've covered some other S2S metrics in previous presentations. I'm not going to cover them here, but just wanted to give you a little bit of eye recognition. Things like Hofmuller diagrams, identifying objects using method for object-based diagnostics in the lower left, TC genesis density functions, relationships between two fields in the model, in this case moisture and precip, and then the space-time coherence spectra diagram. So those are, there's quite a few presentations about those. In the interest of time, I wanted to just kind of dive into how we have been working our way through trying to take community contributions and merge it into METplus in a way that allows for reuse of the tools that are already available in METplus, but still the flexibility for the community contributions. So what we're doing is many of the process-oriented diagnostics are taking full advantage of the entire framework. So using components, not only the core statistical computations in MET, but also the Python libraries that are also underpinning METplus. So typically we're using the MET tools for a lot of the pre-processing steps. And then we are doing the indice and diagnostic computation in Python, either integrating it into METcalc directly or keeping it in a contributed code area within METcalc. The graphics are, the generation of plots and so forth are computed or plotted in METplotPy. And then if there's statistics that need to be computed from the output, say for instance anomaly correlations or something like that, then we pull that back in under MET using the stat analysis tool to compute those. Much of this is then driven using what's called a driver script or a user script. So here's kind of an example of how the data flows through to handle these process-oriented diagnostics. So MET is used for the ingest and pre-processing, example, computing monthly means or something like that. And that output is then daily mean if they're needed, cast into what library called METDataDB, which handles data ingest and so forth. We're in the process of renaming that probably to something like METDataIO or METDataUtils and so forth. Once the data are read in, they are then converted into an X array and passed over to METcalcPy, where the indices and diagnostics are computed. And then those are then made available to METplotPy for plotting. And if they are, once again, if there's things like anomaly correlation or skill scores that need to be computed, then those are passed back into MET for the computation of the skill scores. You may ask yourself why is this so complicated? Because it's really kind of easy to just write a Python script and compute what you need. There's a couple of overarching reasons for the complication. One of them is general standardization, being able to read in the data in the same way, especially when you're talking about an operational system. Having standard data ingest is pretty critical. Additionally, the whole point of METplus is to have the computation of the statistics be computed by the same package over and over again. So we need to figure out a way to have that statistical computation, computed exactly the same way, regardless of what platform you're computing on or what organization you're with. And then finally, having standardization of plotting, once again, so that the output is presented in a cohesive manner. Additionally, there are operational constraints, and we are definitely butting up against these pretty routinely. As per NCAR requirements, there's a limit of the number of Python packages that can be brought into the operational environment. And so that is, one of the lifts on the development that we need to work with routinely, and trying to make the community contribution something that NCO can accept. Finally, our focus is on providing flexibility and reusability, so that many times when we're getting community contribution, we're seeing hardwiring in the contributed code, things like field names or the sample size or thresholds that are used. So we need to work with that code in order to remove that hardwiring, as well as trying to look for consistency and ways to reuse the tools. For example, the computation of monthly means for heights many times are the same as for temperature and winds and so forth at different pressure levels. So we're trying to pull out that core computation and make it accessible to all of the algorithms, rather than just having it embedded in each one of the community contributed codes that we get. Okay, so here's just one look at the RMM MJO index use case, and once again, I'm not going to dive into the details of this, just kind of cover some of the high level information. You can go back to the presentation to get into the weeds on this if you'd like. But the data are provided in the use case, as well as the EOFs. There are pre-processing steps, so we're using MET PCP combine and regrid data plane. The PCP combine tool computes the daily means and the daily annual cycle as well, and then we use regrid data plane, which is a regridding tool, to cut the domain down to the 15 to 15 degree latitude band that's needed. And then we pass the data into METcalcPy to compute the anomalies and so forth, and then that also goes on to compute RMM. And then it gets passed into METplotPy for the plotting of all the different diagrams, the phase diagrams and the time series and so forth. Additionally, and I'm not going to go through all the different calculations, but I did want to point out in this case, the code that was passed over, we did add in a lot of different configuration options, including being able to run for the information needed just for forecast or for the analysis. In our case, we call it OBS, or for both. And then the number of observations per day, being able to pass in EOF file names and so forth. adding in configuration to allow for normalization and more plotting specifics, and being able to write the data to particular directories and read them in from directories that are not hardwired. So same thing, we have an OMI use case. Once again, here, most of these are the details on how we're passing the data through the tools. Once again, using PCP Combine and regrid data plane as pre-processing, and then passing it in METcalcPy and METplotPy for computation and plotting. Then also another diagnostic that we have that was added a while ago, but we've done some additional flexibility, added some additional flexibility to it, is blocking. And so same thing, there's pre-processing steps that are performed in MET, and then it's passed into METcalcPy to compute the central blocking latitude, the instantaneous blocking latitude, and the group IBLs, and then it's passed over to METplotPy for plotting. I should note in the lower portion of the slide in yellow is which organization contributed these codes. And so then what we've recently added is passing the IBLs back into stat analysis to compute contingency table statistics, categorical statistics regarding the IBLs and the blocking frequency and so forth. So here's just examples of the plotting. Everything's coming off of 500 millibar heights. Central blocking latitude is derived after there's a high pass filter that has been applied, and then over here there's an example of the blocking frequency with respect to longitude, and then the frequency for both instantaneous and grouped blocking latitudes. And then passing that into stat analysis, you can see that we can compute statistics like critical success index, which is the threat score, our frequency bias, probability of detection, probability of and false alarm ratio, and so forth. Okay, so then also weather regime analysis, also contributed by Wang and Lee at University of Illinois Urbana-Champaign. Similar things. We have the pre-processing, and then we use METcalcPy for the computation, and we have brought out the capability of being able to apply EOFs or to compute EOFs. So that is now something that is routinely available within METplus. And then once again, we added in the passing of the data into stat analysis to compute multi-category categorical statistics with regards to the regime classification and the regime frequency. So here's just an example of the EOFs. So we're derived from a 17-year data set. And then these are the different regime classifications. So there's regimes 1 through 6 for both ERA and GFS. And then also plotting of the frequency of the number of weather regime days per week with regards to the different weeks within the winter months for both ERA and then for GFS. And then here's an example once again of computing different statistics, in this case the frequency correlation for each one of the weather regimes. So that's just kind of showing you that it's kind of a mix of using core MET tools plus Python in order to get to the end result. This is work in progress. It is focused on trying to put in some additional core capability of computing zonal and meridional means. Sorry, I can't say that very well. And this is contributed by Butler and Lawrence. That should not say UIUC. I'll correct that. That's PSL. And it's focused on stratospheric, sudden stratospheric warming and so forth. So we do have the use cases in to show how you can compute zonal means or meridional means. and the examples are for winds and temperature and so forth, but that can be extended to geopotential height and other fields as well. We have also added in a lot of capability with regards to marine and cryosphere evaluation, including verification using satellite fields for sea surface temperature, sea surface salinity, sea surface height, and ice cover or concentration. And then also looking at doing some baselining with regards to some of the statistics that CPC routinely uses. So we now have the ability to ingest the CFS v2 fields, and we did some baselining with CPC. We found that there were some rounding differences between their computational Breyer scale score and METplus's version, and then we found that there were also differences in how we were handling climatologies and ensemble data. And so when we were working on developing some new tools for ensemble verification, which I don't have time to go over in this presentation, we did add in the ability to normalize anomalies from climatologies for the ensemble data and the computation of Breyer score based on these, as well as the ability to read ensemble members from one file, which prior to a lot of this work, we were anticipating that each ensemble member would be in a different file. So that has been updated. We also recently diagnosed some additional capability that's needed to support how CPC uses Heidke scale score, especially looking at like temperature anomalies and so forth. And so that has actually been written up as an issue and is in our development pipeline and will be in the next release. So if you work routinely with CPC, within the next 6 months, hopefully you will have some of the core components of how they do their evaluation available to you through the METplus package. We also started working with CPC on something that's a little bit more, cutting edge, looking at their week 2 hazard forecasts, looking at their weather warning areas, and we focused it on cold hazards at the 8-day mark. We used mode and worked with Justin Hicks at CPC for him to be able to identify mode objects within the WWA fields, and then looked at how those fields could be used to compute diagnostics like the medium of maximum interest, which is a different, kind of a summary diagnostic for mode, looking at all the different attributes of the objects. And right now, CPC is in the process of working with forecasters to get their feedback and develop a website so that they can start using this more routinely in actually more of a model diagnostic and almost product type of scenario rather than using it as a verification source. So what's upcoming? Right now in the pipeline, we have additional marine and cryosphere capability that we're adding in, using scatterometer winds and altimeter wave heights for additional sources of verification. We're continuing on with getting the stratospheric warming work done with Butler and Lawrence. We have a deliverable for the UFS R2O project to get gravity wave drag verification, some use cases developed. We're still looking for some expertise in that area. So if that is an area that you have expertise in, please email me and let me know. We would love to at least just understand the data sets, get some sample data and understand what needs to be put together. We're also working with Professor Dürrmeyer at GMU on integrating his coupling index into METplus, and we were just recently found out that we're part of a project that was awarded by JTTI to start adding in additional land surface modeling type of observations for evaluation purposes. And then we're also working with Dr. Stan at GMU on some ENSO indices and looking at the MJO Kelvin wave interaction with the ENSO. and then still working with Dr. Diaz and Dr. Gainey at PSL, looking at adding the mode time domain capability to look at zonal and meridional phase speeds of precipitation fields and use that as a diagnostic, which should be pretty interesting. I also wanted to take a couple minutes to just point out to you that there is a full set of final metrics that were derived from the DTC UFS metrics workshop. Back in February 21, we put in a lot of work on it and put out the final list in the October-November timeframe. You can go to this website to check that out. Here are the diagnostics that were identified for the S2S application, and they're broken down by tier based on the things that are the metrics that are included in tier 1 should be evaluated routinely, like every time you're starting to move from one gate to another as far as development cycles go. When you get closer to the operational part of the R2O process, then you should be looking at tier 2 as well as tier 1. So it's kind of adding in some additional diagnostics. And then as you get closer and closer to operations, the plan is to also look at all of these tier 3 and tier 4 metrics. And so we have, the capability to compute some of these diagnostics. I'd probably say about, maybe like half of them at this point. But we also have a gaps analysis on our website as part of that metrics page. And you can see here that we do have support for some observation types or analyses types, as well as several metrics that we still need to include in METplus, including fire danger index, AO, AAO index, NAO, MPNA, Palmer drought index, Eastern Asian summer monsoon index. So those are all indices that we still need to work on, and so we will need partners to collaborate on those. Okay, so that was a lot of information. I wanted to leave time for questions. Thank you for your attention. I do want to call out that we are having a METplus users workshop this June, the 27th through the 29th. It will be virtual, it will be free. Registration and abstract submission is now open. So go ahead and check out the website and register. And if you're using METplus at this point, we would strongly encourage you to submit an abstract to demonstrate in a presentation how you are using it, so that others, especially within this particular area of emphasis, can learn from what you've done. And once again, just want to thank all of our sponsors for DTC, as well as for the NCAR and GSL nodes that have contributed to this. So questions?
Thank you, Tara. I know that there is one question in the document here. I'll go ahead and just read it to you. For MJO-related calculations, it is challenging to calculate anomalies from models since we don't have sufficient samples to build up model climatology. How does METplus handle this?
So, we are following, expert advice. So we work with those of you in the community that can tell us, how long of a sample size we need and so forth. The nice thing about METplus is because of its flexibility, to compute climatologies and so forth, it will just read the whatever number of files you pointed to for the computation of those climatologies. To read and to develop a 30-year climatology, it will require a lot of computation to do that, and that's understood. If there are climatologies that are already that have already been developed, it's our goal to have METplus be able to read those climatologies in. So that's kind of a wishy-washy answer, but to be honest, we hope that the tools are flexible enough to allow the scientists, like yourself, to develop the climatology the way you need it to be developed. Hopefully that answers your question.
Okay, thank you. I don't know if there are any other questions for Tara. I see Kathy's responding to yet another one on hers, but if anyone else has any other questions for Tara, please enter them into the document here. And if I don't see anybody typing right away, we'll go ahead and call it a day. But if anybody has any questions now or very soon, go ahead and type it in the document, and we'll make sure that Tara sees it and can answer in the document as well. So I would like to personally thank both of our speakers today. Wonderful talks, very informative. And thank you to everyone else for showing up and spending your time listening to these talks. So thank you very much, and we will see you next month. It will be the first Monday of June. I'm not sure the exact date of that, but we should have 2 more talks lined up, so keep your eyes and ears peeled for that as well.
Thanks, Mark.
Thank you.